In Module 1, we focused on static optimization, problems where all decisions and outcomes are determined at a single point in time. However, many of the most interesting and important questions in economics are inherently dynamic. How should a firm invest in new capital over several years? How should a government design fiscal policy to stabilize the economy over decades? How should a consumer decide how much to save and consume throughout their lifetime? Dynamic analysis is concerned with the evolution of variables over time, and the tools we use, differential equations, difference equations, and optimal control theory, help us model and solve these problems. Two main approaches dominate. Continuous time models, time flows smoothly, equations use derivatives. Discrete time models, time moves in steps, equations use recursive relationships. We will begin with the building blocks, difference and differential equations, and then move into dynamic optimization. 2. Difference equations in economics. Difference equations describe how a variable changes from one period to the next. These are particularly important in population growth models, cobweb models of price fluctuations, capital accumulation in discrete time, inventory management. 2.1 First-order difference equations. A first-order difference equation links the current value of a variable to its value in the previous period. For example, a simple savings equation could state that next period's capital equals this period's capital plus savings. The general solution involves finding the equilibrium or steady state, where the variable stops changing. Analyzing stability to see whether the system converges to, diverges from, or oscillates around the steady state. 2.2 Higher-order difference equations. Economic processes often depend on more than just the immediate past. For example, investment decisions may depend on expectations formed 2 or more periods ago. Higher-order equations can produce richer dynamics, including cycles and complex oscillations. 3. Differential equations in economics. In continuous time, we use differential equations to describe changes. For example, the Solow growth model uses a differential equation to describe how capital per worker changes over time. Models of continuous price adjustment describe how prices move toward equilibrium. 3.1 First-order differential equations. A first-order differential equation relates the rate of change of a variable to its current level and possibly other variables. Solving involves finding a particular solution for a given initial condition, identifying steady states, examining stability properties. 3.2 Systems of differential equations. Many economic models involve multiple interacting variables, for instance, capital and labor, or inflation and unemployment. Such systems require simultaneous solution and phase diagram analysis. 4. Dynamic optimization. Dynamic optimization seeks the best time path of decisions when outcomes depend on past and future actions. Two main approaches are optimal control theory, typically used in continuous time. Dynamic programming, typically used in discrete time. 4.1 Optimal control theory. In continuous time, the decision problem is often framed as maximizing an integral over time subject to differential equations describing the system's evolution. For example, a firm might want to maximize the present value of profits over an infinite horizon. A government might want to maximize social welfare subject to capital accumulation constraints. The Pontryagin maximum principle provides necessary conditions for optimality. It introduces co-state variables, which have an economic interpretation similar to shadow prices in static optimization. 4.2 Dynamic programming. In discrete time, dynamic programming is the main tool for solving intertemporal problems. The Bellman equation expresses the principle of optimality. An optimal policy from today forward is composed of an optimal action today plus an optimal policy for all future periods. Applications include the consumption savings problem, inventory management, pricing strategies for durable goods. Dynamic programming has the advantage of handling problems with uncertainty and nonlinearities more easily than traditional calculus-based methods. 5. Applications of dynamic optimization in economics. 5.1 The Ramsey growth model. This model extends the Solow model by explicitly modeling household preferences and optimizing consumption over time. It provides insights into optimal savings rates, How economies converge to their steady state. The trade-off between current and future consumption. 5.2 Optimal extraction of exhaustible resources. This models how much of a resource should be extracted in each period to maximize present value. The result, often referred to as Hoteling's rule, states that the net price of the resource should rise at the rate of interest. 5.3 Investment in human capital. Dynamic optimization is also used to analyze the optimal allocation of time between work and education, balancing immediate income against future earning potential. 6. Game theory in advanced mathematical economics. While optimization considers a single decision maker, game theory examines strategic interaction among multiple decision makers, each optimizing their own objective function. 6.1 Static games. These are games where players make decisions simultaneously without knowing the other's choices. Key concepts. Nash equilibrium: no player can improve their payoff by unilaterally changing their strategy. Dominant strategies: strategies that yield better outcomes regardless of others' choices. Mixed strategies: players randomize over possible actions. 6.2 Dynamic games. These involve sequential moves, where timing and information matter. Types. Perfect information games: all players observe previous actions, e.g., chess. Imperfect information games: players make decisions without knowing all prior moves. Dynamic games often use subgame perfect equilibrium, found by backward induction. 6.3 Repeated games. Economic relationships often repeat over time. Employers and employees interact every day. Firms repeatedly compete in markets. Repeated games allow us to model reputation, trust, and punishment strategies. 6.4 Applications of game theory. Oligopoly pricing strategies. Auction design. Trade negotiations. Environmental agreements. 7. General equilibrium analysis. 7.1 From partial to general equilibrium. Partial equilibrium examines a single market in isolation. General equilibrium looks at all markets simultaneously, capturing how changes in one market spill over into others. 7.2 The Warration model. The Warration general equilibrium framework shows how prices adjust to balance supply and demand across all markets. The existence of equilibrium is established mathematically under certain assumptions about preferences, technologies, and endowments. 7.3 Welfare theorems. 2 fundamental results. First welfare theorem: under perfect competition, every competitive equilibrium is Pareto efficient. Second welfare theorem: any Pareto efficient allocation can be achieved by a competitive equilibrium with appropriate lump sum transfers. These results are cornerstones of economic policy analysis, showing the conditions under which markets deliver socially desirable outcomes. 8. Computational tools for advanced mathematical economics. Modern economic research often involves problems too complex for analytical solutions. Computational methods bridge this gap. 8.1 Numerical solutions to dynamic models. Value function iteration for dynamic programming problems. Numerical integration of differential equations for continuous models. 8.2 Simulation methods. Monte Carlo simulations and agent-based modeling allow us to study systems where randomness and heterogeneity are central. 8.3 Software tools. MATLAB, Python, and Julia are widely used to implement these methods. They allow researchers to solve high-dimensional models, conduct sensitivity analysis, and visualize dynamic paths. 9. Closing remarks on advanced mathematical economics. In this course, we have traveled from foundational mathematical concepts through optimization, dynamic analysis, game theory, and general equilibrium. By mastering these tools, you now have the ability to translate complex economic problems into precise mathematical language. Apply static and dynamic optimization to solve decision problems. Analyze strategic interaction in multi-agent settings. Understand how markets interact in a general equilibrium framework. Use computational tools to tackle problems that are analytically intractable. The skills developed here are essential for both theoretical research and applied policy work in economics. They equip you to think rigorously, to interpret results carefully, and to extend the frontier of knowledge in economic analysis.